Welcome back to day 12 of our explainer. Today, we're firing up the Cyber Command Center to explore the absolute core concepts of cryptography. We're talking about the invisible math that literally shields our entire digital lives from unauthorized access.
Here is our quick boot-up sequence briefing for today. We're going to track the journey of a single message, taking it from its vulnerable plain state, moving into complete cryptographic security, and then bring it back. Finally, we'll wrap up with a look at how this invisible shield protects our daily digital systems.
Section 1. Understanding digital cryptography. Let's just start with the absolute basics and define the fundamental processes that keep sensitive information safe across the globe. Section 2. Converting into secret form. So let's dive right into our very first defense mechanism, which is encryption.
You can think of encryption as your ultimate digital lock. It takes readable data, which, in the cybersecurity world, we just call plaintext, and transforms it into a completely secure, incomprehensible format. And you literally cannot read it without the proper digital key. We call this newly scrambled data ciphertext. Now, its main purpose? It's pretty straightforward. It protects sensitive data and secures communications. So even if an attacker manages to intercept your message, there's no way they can actually read it.
This perfectly illustrates just how vulnerable regular text is out on the open internet compared to the locked-down nature of ciphertext. It's kind of like a classic Caesar cipher where you shift letters down the alphabet. A simple phrase like "meet me after the party" gets transformed into an absolute jumbled mess. To anyone trying to snoop on your connection, it's just random noise.
Section 3. Restoring original data. So what exactly happens when this scrambled ciphertext finally reaches its authorized destination?
Well, that brings us to decryption. Decryption provides the necessary digital key that lets authorized users recover that original data. It's what makes a secured two-way communication channel possible. Essentially, it's just the encryption algorithm running in reverse. It takes that confusing ciphertext and turns it right back into the original plaintext that you can actually read and use.
When we put both sides of the operation side by side on our dashboard here, you can clearly see the sender's encryption phase locking the data and the receiver's precise decryption phase unlocking it. Notice how the secret key is the vital, absolute must-have component on both ends of this transmission pipeline. Without it, the math just doesn't work.
Section 4. The encryption cycle. Let's see how all of this builds into a complete, continuous loop that protects our data both in transit and in storage.
The encryption cycle is a really precise 5-step workflow. First, you have your plaintext. Then it's algorithmically locked into ciphertext, transmitted securely across the network, and finally, unlocked back into plaintext at its destination. You can think of it like a secure tunnel. You put the vulnerable data in, the algorithm snaps the lock shut, the data travels safely as ciphertext, the authorized recipient applies their decryption algorithm, and boom, out comes the pristine plaintext on the exact other side.
As you can see, the digital padlock and key mechanisms work together in sequence to keep a message totally safe while it's traveling. Let's say we start with a simple hello. The encryption key locks it down into a string of completely random characters. Then, the moment it arrives, the matching decryption key unlocks it back into hello. It's a simple concept, for sure, but mathematically, it is incredibly robust.
Section 5. Symmetric versus asymmetric keys. Now, not all digital keys are created equal, right? So we really need to understand the two primary cryptographic methods that modern systems are using today. There are two absolute titans of encryption. First up is symmetric encryption. This is where you use one single shared key to both lock and unlock the data. It's incredibly fast, which is great, but it does carry a key distribution risk. Basically, if a hacker intercepts that shared key, the whole system is compromised. Then, on the other hand, we have asymmetric encryption. This uses a mathematically linked pair, a public key and a private key. This completely eliminates the risk of sharing secret keys, though because the math is so complex, it is a little bit slower to process. Let's look at how that asymmetric architecture actually functions in the real world. Literally anyone can lock a file using your openly available public key, but only you possess the top secret private key required to decrypt and read it. Get this. Even the sender who locked the message cannot unlock it once it's sealed. This brilliant setup is exactly how we can safely communicate with brand new servers on the internet every single day, without ever having to securely exchange passwords first. Section 6. Real-world application summary. So you might be wondering, why does all of this abstract math actually matter to you outside of this Cyber Command Center? Well, every single day, these invisible encryption cycles are operating relentlessly behind the scenes. They are securing everything from your WhatsApp messages to your online banking transactions, e-commerce payments, and your cloud storage vaults. Whenever you see HTTPS in your browser or when you use an end-to-end encrypted messaging app, you are directly utilizing these exact complex symmetric and asymmetric algorithms we've just been talking about.
To quickly summarize our Day 12 explainer, these two distinct processes, locking and unlocking data, form the absolute bedrock of all modern secure communication systems. Without encryption converting plain text to ciphertext and decryption converting it back, the internet as we know it for commerce, private conversations, and secure data storage simply would not exist.
But with quantum computing looming on the horizon, it leaves us with a truly fascinating question. How are our encryption algorithms going to need to evolve to protect our privacy against the ultimate digital lockpicks of tomorrow? It's a crazy thought, right? The cat-and-mouse game of cybersecurity literally never ends. Thanks for joining me in the Command Center today to explore this, and I will see you in the next explainer.